Now we're going to go through the instruction set architecture's 2 practice problems. So the first question here was about branches and constants in instruction encoding. First part of the question is what information we need to encode to be able to do this sort of an instruction. And the second question is why can't we do this in MIPS? So let's take a look at this. To encode branch equal, if R2 is equal to 7, we jump to loop, what do we need? Well, we need an opcode, that's branch equal. And if we look at the MIPS instruction encodings, we have 6 bits for the opcode. We need one register, that's R2, to see if the registers are equal. And we can see that'll take another 5 bits to encode the register. And then we need 2 constants. We need a constant for 7 and a constant for loop. And we can see over here that we have 2 formats that have 1 constant each. So now the question is, why can't we have this in MIPS? And the answer is that we don't have 2 constants in any of these. But more importantly, why don't we have 2 constants? So if we want to have 2 16-bit constants, we need 32 bits. So here in the I format, we have space for 1 constant, either a jump address or an immediate value, and that's 16 bits. If we wanted to have 2 16-bit constants, we'd end up using all of our 32 instruction bits. We wouldn't have any room for the opcode, we wouldn't have any room for the register. So we can't encode this sort of an instruction in MIPS because we don't have room to put 2 constants in our instruction. Now let's take a look at a question about branches and setting the addresses for them. So the first part of this is to identify where the jump branch should go, and the second part is to fill in the constant needed to jump to that point. So what this code should do here is we set I to equal to 0, which is in T0, we set T1 to 10, and then we're going to go around, we're going to increment I or T0 by 1, so add I, 1, keep going around until we've done it 10 times. So if you look at the control flow that's going on here, we say set less than, so T2 is going to be 1 if T0 is less than T1. So this is going to be true if our count here, T0, is less than our value over here, 10. So whenever this is true, we want to go around again. So we're going to branch not equal that value in 0. So whenever this was true, so whenever we're less than 10, we want to go around the loop again. So we're going to want to jump from here back up to this instruction over here. And the question is, how far do we need to jump? So we're going to jump from this instruction back to this instruction, and now that's going to be minus 3. So we want to jump back 3 instructions. Well, 1, 2, 3. You'd think minus 3 would bring us up here, but remember how this is computed. We always do this PC plus 4. So we're always going to add 1 instruction no matter what we have here. So this is really going to be minus 3 instructions plus 1 instruction. Now remember also that we're talking about different things here, instructions and bytes. So this is a minus 3, and that minus 3 is going to be shifted over by 2, which is multiplied by 4, so it'll be minus 12, and then it's going to have 4 added to it. So we take this minus 3, we shift it over by 2, that's multiplying by 4, so it becomes minus 12. If you look where minus 12 will get us, it'll get us up to this instruction, and then we do PC plus 4, which will get us to that instruction. So minus 3 here is going to get us to the right location. All right, next one here is about loop addressing. So here we have code that's going to go through a bunch of memory and decrement each word value. And we're 2 jobs here. One is to add the missing jump instruction to go around the loop, and the other one is to add a branch that exit early if the value read is 0. So let's take a look at our code. We go, here's the array size, and here's the initial variable that we had there. So we're going to load the variable and decrement it. We want to do this for every variable. Then we store the value back. So we subtracted 1 from it, and we wrote it back to memory. Now we go on to the next value and the next address. So this is keeping track of how many we've done. This is keeping track of the address. And then if they're equal, we're going to exit. So this is saying if we're at the end of the array, so we've gone all the way to the end of this here, we're going to exit it. So here's the value. This is the total amount of stuff in our array. And then here's exit. We go and we do our first instruction outside the loop. So what's missing here is there's nothing that says keep going until we've run out of stuff. All we have here is something that says when we're done, exit. So let's take a look at how we need to modify this. So to add the missing jump instruction, we're going to put this down here. If we're at the end, we exit. If we're not at the end, then we want to jump back up and continue the loop. So go around and do the loop. The other part over here is to check if the value is 0. So here we've loaded our value, and we're going to check if it's 0, and if it is, we're going to go right to the exit. So here are the 2 instructions we'd have to add to fix this. So this loop instruction means we go around and around again until we get to the end. When we get to the end, our counter here equals the address of the last bit in data, and then we'll go to exit. The other thing we wanted to do was exit the loop immediately if we loaded 0. So here's where we load the value, so we just check if we loaded 0, and if we do, we go immediately to the end. All right, So now here's the next problem, and this is about procedure calls. So if you look at what we have here, we have a main program that's going to call this manipulate program, manipulate procedure. The manipulate procedure is going to do something, but it's also calling this double procedure, which is doing something. When double is done, it's going to return back into manipulate, finish manipulate, and manipulate's going to return back to main. So that's what we want to have, but there's some problems here. None of these are following the register conventions for arguments or results. So if you look at manipulate here, it's expecting its inputs to be in T0 and T1. But if we look at what's happening over here with main, it's putting its data in T4 and T5 for manipulate. So we don't have the right register convention, we're not going to get the right data to the right place. Also, none of these are saving the necessary temporaries on the stack. If you go to use a variable like T4 here, you need to save that before you jump into a procedure, and main isn't doing that. And finally, the program's never going to exit, and it's not going to exit because we didn't save RA at any point here. So let's go through and fix this up. So before we do that, let's review the MIPS register conventions. So the results are put in the return values here, V0 and V1 from a procedure. A0 to A3 are the arguments. This is the data that goes into the procedure. And then the rest of the registers are divided up between caller save. So these are registers that have to be saved by the caller if it uses them, and callee save. These are registers that are saved by the procedure that's being called if it uses them. So let's see how we go ahead and apply this. So here's main, what do we need to do to it? And here's manipulate, what do we need to do to it? So for main, the first thing we need to do is we need to make space to save T4. So T4 is one of these caller save variables, or registers, sorry. So it uses T4 here, and it uses T4 again after it does the call. So we need to save that across the call in case manipulate uses that. So we go ahead and make stack space to save it, and then we're going to do the same thing by restoring it. So we're going to load it off the stack and put the stack back when we're done. Now, why didn't we do anything about T5 here? Well, if you look at T5, T5 is never used again after this call. So we don't care if manipulate writes over it. Only T4 since we reuse T4. Then we need to make sure that we put our arguments in the right place. So the arguments that we want to send in to manipulate need to go into the argument registers A0 and A1. So we go ahead and we say, well, they were in T4 and T5 before. We're going to go ahead and move those into A1 and A0. So this is just copying them into it. And finally, the result from main needs to be put in the result register in case somebody else is calling it. Or sorry, the result from manipulate is stored in V0, and so if we want to do something with it in main, we need to get that value from V0. Okay, let's take a look at manipulate. So first thing we did in manipulate here is we went and changed it so that it's using the right arguments. So instead of getting its values from somewhere else, it's now getting its values from the argument registers. And when we're done with it, it's also going to put the results back in the return register here, but it's also getting the results back from the value registers from this function. So double here returns its values in V0 and V1. These are return registers, and they're going to be used here by this function, manipulate. So we need to change it so it uses the right registers coming back from that procedure call. Now we need to save some stuff here. So we need to save two things. We need to save T2, because we've used it here before the call to double, and we use it after the call to double. And we need to save RA, because when we jumped into this procedure, RA was where we need to jump back to. But when we jump into double, RA is going to be set to jumping back to here. So this jump return here needs to get the right value, the value before we did this jump in link. So we need to save RA on the stack, and then when we're done, we need to pop RA back off the stack so that we return to the right place. And finally, the last thing we need to do is make sure that we take the values that we want to send to double and we put them in the right argument registers so double will get them. And of course, the last thing here is that since we ourselves are a procedure, we need to put our final results into the value register to return it back. Remember, these results here in this value register, there's what's coming back from double. So we use them, but we return this value in the value register. All right, here's a question about memory indexing instructions. So here's a program that's supposed to go through an array of values and add up all the values there. So let's go ahead and complete the program so it does this, and then we'll look at how we could use another instruction if we had it to make this more efficient. So let's get started here. How do we do this? So the first thing we need to do in our loop here is we need to load the data from the array. We're going to add up everything here. So T4 here is where we're going to load our data into, and T0, that's the address of our array. So the address of our array here is in T0. So we're going to load whatever data is at T0 into T4. Then we're going to add this up. So T3, this is where we're going to store our value. So we're going to say add into T3 whatever we just loaded from the data. And then finally, we're going to go on to the next element in the array. So this is our address in the array. We're going to add 4 to it to go to the next value. And then we keep doing this until our array address equals the end of our array. And when that's true, then we're done. Otherwise, we keep going around. So that's how you do this loop. Now here's another question. How would you do this loop if you had a special load instruction that looked like this? So it loaded data into a register from an address, but then it had this built-in increment into it. So it automatically adds some value to it. Well, this is pretty simple. Now we're going to do our load word. We'll still load it into T4. We're going to say at T0, but now we tell the instruction to increment plus 4. So this instruction is going to do that incrementing for us. Now we go on, we don't need the other instruction which does the increment. We just need the instruction which sums it up. So we've saved ourselves an instruction here if we had this special instruction. Now the last question, how many instructions would be executed with the old one versus the new one? So here we have fewer instructions, so it should run faster. So with the old code, we had 4 instructions in our loop, and the loop ran around 16 times, so it would be 64 instructions. In the new code, if we have the special instruction, we only have 3 instructions in our loop, so we're only going for 48 instructions. So it's 25% faster. And this is why people put in special instructions like this, because they can get a lot of speed ups in very special places with them.